So here's the problem that was given, which is that I like the font type, by the way, it's pretty great. So you've got Luke Skywalker, Princess Leia doing some target practice. Leia is firing a laser from here to this point here and it's bouncing off hitting this target here. And the idea of what we're supposed to see is that basically when you bounce when you look at the direction vectors, so the unit vectors in this direction, so the unit vector in this direction plus the unit vector in this direction, they totally, balance out to be just a vector that's purely horizontal. In fact, let me show you because we can definitely do this work here. So I guess I need to stop sharing. So the whole idea here is that pens. Let me stop sharing so you can see what I'm going to draw. So I have my phone in my pocket, it's just in the way. So the whole idea, right, is that Leia's up here, hanging out at -2, 2. And Luke's here at the origin, and here's the target over here. And she fires her laser this way, pew, 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 bounces off, pew, 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 pew. So here's what they asked us to do. Find the unit vector from Leia to Luke. Right, here's Leia, here's Luke, here's the target. So the unit vector in that direction, right, if we're going this way, well, here's what I know. I know that the vector from there to there is the vector I'm going over 2 and down 2. So 2, -2. I need to normalize this, meaning I need to divide by its length. The length of V is just the square root of 8, right? Square root of 4 plus 4, which is 2√2. So the unit vector in the same direction, which is we're calling U, I believe, yeah, is going to be just each of these things divided by 2√2, which is going to be 1/√2, -1/√2. All right, we're going over and down. The unit vector in this direction, if we're going over and up, well, right, it's going to be in the 1, 1 direction. I think we're calling that W. So it's going to be in the 1, 1 direction, but we have to divide by its magnitude, which is the square root of 2. So it's going to be 1/√2, 1, 1, which is just 1/√2, 1/√2. You should rationalize these if you're being asked to, but it shouldn't be a big deal. So then if we add U and V together, so again, right, U is the unit vector going that way, V is the unit vector going that way, we see that, sorry, U is the unit vector going that way, W is the unit vector going that way. We see that U plus W is going to be this plus this, which is going to be 1/√2 plus 1/√2, which is 2/√2, which is √2. And -1/√2 plus 1/√2 is 0. So U plus W, this direction plus that direction, if you're just talking about the directions that have length 1, is purely horizontal, right? It's totally just going in that direction. And the point is that the direction of essentially the direction the laser is fired in plus the direction the laser bounces off in is going to be perpendicular to what's perpendicular to the reflective surface here. So this is the normal vector here, this vector plus this direction vector plus this direction vector. They do have to have the same length. If you just tried adding this vector to this vector, you would get something that was pointing right, like right, you going from there to there, which wouldn't be purely horizontal. But if you add this direction vector plus that direction vector, it should be perpendicular to the vector that's perpendicular to the reflective surface. So U plus W is meant to be perpendicular to the vector that's normal. Essentially, I feel like the way we're supposed to read this here is that if you add the direction that the laser is fired plus the direction the laser is bounced off in, it should be parallel to the reflective surface if you just add the direction vectors. Interesting. Okay. explain why it's not a coincidence. I think the reason it's not a coincidence is really because, right, like, so just to kind of talk about this, right, if you're reflecting something off, right, like, so if you're starting over here, I'm going to say this point is negative AB, and you go, if you bounce it off some reflective surface that's flat at the origin, eventually you're going to kind of mirror image that, and you're going to end up with the point AB, right? You go from here, you bounce off that, you're going to end up over there. So when you add the two directions together, the down part and the up part cancel each other out, right? This vector being kind of the reflection of this vector goes up as much as this vector goes down. And so it's totally going to be perpendicular to this vector that's perpendicular to that. Right there. Okay, I think that's enough of an explanation. Let's look at part B, or part problem 2, I should say, which is asking that. So basically the same kind of idea, but now we've got a different orientation. One thing I do like about Waldron is I do feel like he really does try to make his problems kind of contextually fun. I definitely graded for him many years ago for a, gosh, was it 21C? I graded for him for a 21C or 21D class, and it might have been up to this class. Anyway, I graded for him. He's a fun guy, not a mushroom, just a fun guy. And it's a lame joke, but it was there. I took it. So here's the next situation. Leia is standing at the point -1, 2. And Luke is standing at the point 2, 1. And his mirror is oriented the following way. It's oriented this way. So that, oh man, did I draw that? No, I didn't. So that the vector that's normal to it is pointing that way. So it's going over 1, down 1. So the normal vector is, I guess I should use a unit vector. Who's calling me? I don't know. No one important. It could. Sorry, I probably should. No, that doesn't look like a real number. So the normal vector is left 1, down 1, so negative, negative. And we'll make it a unit vector. So -1 over 2, -1 over 2. And we want to hit this target. So right here's the point -1, 2. We want to hit this target that's at the point 3, -2. So right, Leia shoots, she scores. So she shoots, laser bounces off, and hits that point right there. I feel like my picture is not, I feel like my mirror picture is not particularly great. My mirror should look, it's got blue. Let's use fun colors. Yeah. So right, my mirror is a little more like that. There's my mirror. Okay. So the question asks, explain why the laser is able to hit a target located at 3, -2. So again, here's what I'm kind of thinking, right? This vector from Leia to Luke, right? That's going over. Let's just talk about the direction. So right, this is the point -1, 2. This is the point 2, 1. We're going over 3 and down 1. So right, the laser vector has a direction. The laser is in the direction of over 3, down 1. And what's going to happen is the reflection is going to bounce it off and kind of interchange those two things. So it's going to go in the direction of 1, 3. So if I'm starting at the point 2, 1, I'm going to go over 1. Oh, sorry. 1. Sorry, I messed this up a little bit. I'm not going over 3 and up 1. I'm going over 3 and down 1. So then when I reflect it, I'm now going over 1 and down 3. That's kind of why this is working. And again, it's because, right, when you add these two vectors together, and we're just going to add them together because they have the same length, so it's perfectly fine. Right? If they have different lengths, it doesn't work out. You could also just add you could find the directions, right? The directions would be these divided by the square root of 10. But when you add the direction of the laser plus the direction of the reflection, you're getting 4, -4. Which is definitely perpendicular to the normal vector here, right? So the direction of the sum of these two is the same as the direction of the mirror, which is perpendicular to the perpendicular vector. So basically, now, and I kind of took a shortcut, right? Because I didn't normalize both of these. I just said, well, they both have the same length because, right, they both have the length of the square root of 10. So I'm just going to add them together. But you could have said, I'm going to divide this by 1/√10. I'm going to divide this by √10. And you get that this is, right, still works out to have the same direction. Yeah, it's kind of neat. And then the question further asks, find one other point the target could be located where it would still be hit by the laser. So basically, I think that question is kind of the nicest question you could ask, because basically they're saying you could just travel along this path even further. So I feel like the easiest answer would be say, well, I know that the reflection direction, I'm going over 1 and down 3, so just go over 1 and down 3 again. So instead of the point being at 3, -2, I can go over 1 to 4 and down 3 to -5. So another point that would totally work that you can hit with that laser would be, that reflected laser would be 4, -5, because if you bounce off, you can keep going in this direction until the laser peters out. So kind of an interesting question. Basically, the whole idea is that if you're bouncing a laser off a mirror and you add the directions that have the same length together, right? They have to have the same length for this idea to work. When you add their directions together, the resulting direction should be also in the direction that the mirror is, a direction parallel to the mirror direction. Or you could also say the direction is perpendicular to the normal vector, but that's saying if you're both perpendicular to the same vector in 2 dimensions, you're in the same direction. Okay, that's a good question. Maybe we'll come back around to this a little later today. Let's talk about the other question. Oh, good. Yes. Question. I thought this question was an interesting question. I think it was on, someone said it was on the quiz they took, and it was a little bit out there. So here it is. I feel like this one comes from chapter 13.3, which people might not have really covered. Let's see, I did write it down here. Where'd you go? Okay. Let's see. Yeah. So the location of a bird rising on some air, hot air or something, is given by the following terrible equation. R of t equals, I'm going to write it as a vector, sine of t minus t cosine of t. I'm pretty sure the next part is cosine of t plus t sine of t, although the person writing it accidentally wrote an equal sign there, but I feel like right, equals is when you forget to push shift for plus, so I'm pretty sure it was supposed to be a plus. And then 4t squared. Or it's sine t minus t cosine t I plus cosine t plus t sine t j plus 4t squared k. And the question, and that's when time is not negative. And they ask us, how far does the bird travel? So again, this is the position of the bird. How far does the bird travel from time equals 0? I feel like the question was not phrased super well. It's from 0 to t. I feel like it's not good to use t as the end place when t is the variable. So I'm going to call it like t star to indicate that it's like a particular value of t, whereas the variable t is a variable. And then the second question was, how far has it traveled? Has the bird traveled when it reaches a height of 100 meters? So this question is a trick question. I mean, it's not a trick question, but it's really you're going to find the answer to how far it travels when you know what time it is. But then they're asking how far it travels when you go height it as well. The k coordinate or the z coordinate is the height coordinate. So when this equals 100, well, 4t squared equals 100, 4 times 25 equals 100. So when this equals 100, that means time is equal to 5 seconds. So this is really just a complicated way to say time equals 5. Okay, so that's the 7. So to find the answer, we have to remember the arc length formula, which is kind of a pain in the butt. The arc length formula for this position vector with 3 coordinates is the integral from a to b of the square root of dx dt squared plus dy dt squared plus dz dt squared dt. Or alternatively phrased as, it is the integral from a to b of the magnitude of the velocity vector dt. Right, so when you take the velocity vector is the derivative of the position vector, so it's all these derivatives, but then the magnitude of the vector is the square root of all the things squared, which is exactly the square root of all the components of the velocity vector squared. Okay, so R of t again is, where'd you go? I should just hold this in my hand, that would be smart. Sine of t minus t cosine of t, cosine of t plus t sine of t, and 4t squared. The velocity vector is just the derivative of that. So let's see. The derivative of sine of t is cosine of t minus the derivative of t cosine of t, we use the product rule. That's going to be 1 times cosine of t plus t times negative sine of t, or minus t sine of t. The derivative of this is going to be negative sine of t plus 1 times sine of t plus t times cosine of t. And the derivative of this is 8t. Now, notably, the first coordinate just ends up being t sine of t. Right here. So v of t is t sine of t. First coordinate. Second coordinate is t cosine of t. Third coordinate is 8t. So now we can find the magnitude of v of t, which is just the square root of all the derivatives squared. Derivatives squared? No. We already took the derivative. Sorry. Of all, right? So this is right. This is your dx dt, dy dt, dz dt. So the magnitude of this vector is just all of those things squared added together in square root. So it's t squared sine squared of t plus t squared cosine squared of t plus 64t squared. Okay, this simplifies real nicely. I can factor out a t squared. So I got the square root of t squared times sine squared of t plus cosine squared of t plus 64. That's just 1, so 1 plus 64 is 65. So here's what we got. We got the square root of 65t squared. And since t is positive, we can just say that this is t times the square root of 65. Well, that turned out very nicely. So now, the length that we're trying to find is going to be the integral from, you're starting at the bottom when t equals 0 to t equals t star of t times the square root of 65 dt. That's super straightforward to integrate. That's just t squared over 2 times the square root of 65 from 0 to t star. And then it feels kind of weird to plug this in. It's just going to be t star squared times the square root of 65 over 2. So if you know what time it is, that's how far the bird traveled. And specifically when time is 5 seconds, meaning the height is 100 meters, I think was what it was given in. We know that the distance traveled is some gross number. It's 5 squared, so 25 times the square root of 65 all over 2 meters. It's kind of interesting. Clearly, this problem was definitely very well thought out, right? Someone definitely worked to make sure that this definitely had a velocity vector whose magnitude turned out to be very, very convenient to simplify. Okay. Let's see. Let's talk about a couple limit problems. Also, speaking of which, I haven't graded the quiz you guys did for me. If you did it, I will grade it probably tomorrow, and I'll also post solutions to it so you can look at those if you want to. Sorry, at the end of the quarter, things always start to stack up. Like, oh no, I got a bunch of stuff to do. So I will try to make sure that gets done tomorrow. Yeah, that's that. So just a couple things about limits for a second. So for example, if I have the limit as x approaches, x and y. Approaches, I don't know, something like, I know there's a problem kind of like this on the exam. Let's say we're approaching 2, 1. Now I have to make something up that's going to work. Sure. Yeah, that will be fine. And then, I don't know, x squared. Sorry, now my brain is like, sure, James, make it work. Minus xy minus 2y squared. Maybe. I don't know. Let's see. That work. Yeah, that works. Okay. So let's say we have this limit. If you plug in 2, 1, you're going to get 0, 0. 0 over 0, sorry. Right? If I plug in, let's double check. 4 minus 2 minus 2. Yep, that's 0. 2 minus 2, that's 0. So you could try finding paths. The hard thing about this is it's actually work to find paths to the point 2, 1. I know that y equal to 1/2 x would work. It'd probably be easier if I just said x equal to 2y. Although that's kind of a dumb one because if I do plug it in, I'm actually going to get literally 0 over 0. So yeah, that's I could try the path x equal to 2. That's a path that goes to the point 2, 1. So I try that. I have the limit as y approaches 1. Let's see. So x is 2, so I've got 4 minus 2y minus 2y squared all over 4 minus 2y. And now we might try to factor. Right? I can definitely see factoring out a 2 from the top and the bottom. I feel like I've made a mistake somehow here. But oh, yeah, that should be a 2. Now, thank you, Maria. Yes. But I was just checking. I'm like, if I plug in 1, I should still be getting 0 over 0, and I'm not. Yeah, so it should be a 2 minus 2y. If I plug in 1 here, it's still 0 over 0. I can definitely factor out a 2 from the top and the bottom. That's going to give me a 2. In fact, let's factor out a negative 2. Let's make our lives simpler. Factor out a negative 2. I'm left with a positive y squared plus y minus 2. Factor out a 2, negative 2 from the bottom, I'm left with a y minus 1. And then I can see that this part here does factor as y plus 2 times y minus 1. So the y minus 1's cancel, and you get a y plus 2 as y plus, or these cancel as well. So you're getting y plus 2 is y plus 1, so you're getting 3. So at least along this path, we're getting an answer of 3. And the idea, so the problem here is that if you're not going through 0, 0, you probably don't have a good shot at exploiting the different paths to get it to not exist, because it doesn't usually end up working out this way. What's really happening here is that this whole thing does in fact factor. You can find this, the limit as x, y approaches to 1 of, I really want an x minus 2y to factor out. So I'm going to try and make that happen. So typically, right, if you have something in the denominator that's equaling 0, right, if you plug in 2 for x and 1 for y, x minus 2y is 0. That's what you want to factor out from the numerator if possible. So I'm going to try and see, can that happen? If I have an x minus 2y, what else do I need? Well, I need an x times an x, so I need an x there. And I need a negative 2y times a y, so I need a plus y there. And then I need to hope that the middle term actually is what it is. So the middle term is going to be negative 2xy plus xy, which gives me a negative xy. So it does work. Which means I can then cancel these and say that the limit as xy approaches 2, 1 of x plus y is just 2 plus 1, which is 3. So for these limit problems where you're going through a point that is not the origin, often it's going to, if it's a 0 over 0 type, often the limit is going to exist, and it's going to somehow work out that you can factor and cancel stuff here. That is usually what's happening with that kind of problem. Not always, 100% of the time, but often. So often that it's hard for me to come up with an example where it doesn't work. I suppose I could try. Let's see. So I'm going to think of something stupid. It might be totally bonkers. Well, let's look at something like the limit as xy approaches 1, 1. And we're going to make sure that it's a 0 over 0 type. So I'm going to make the denominator. So that's interesting. Let me think about that. Okay, well, fine. So let's make the denominator x squared minus y squared. And let's make the numerator, okay, I think this will not work, maybe, I don't know. Let's say the numerator is x plus y minus 2. Definitely 0 over 0. I'm going to make the numerator, I feel like let's make the denominator even simpler. Let's just make the denominator x minus y. So definitely 0 over 0. But they definitely don't see a way to factor anything out here. So let's try some paths. So what are some paths that go through 1, 1? Well, y equals x. The nice thing about 1, 1 is a lot of paths do go through it. Y equals x squared, y equals any power of x. You can also try y equals 1, x equals 1, and see what happens. It could very well end up being that we just have like division by 0 most of the time, which might be kind of bonkers. Sure, yeah. So let's try y equals x seems like a bad idea, right? Because y equals x will just make the denominator 0. So that's probably not a good choice. Let's try y equals 1, see what happens there. So if y equals 1, you get the limit as x goes to 1 of 1 plus, x plus 1 minus 2 over x minus 1, right? This is y equals 1. Well, that actually works out. Make the limit as x goes to 1 of x minus 1 over x minus 1, which is 1 over 1, which is 1. Okay. Let's try, I'm afraid to try anything else, to be honest. Let's try, I'm going to try something like x equal to y. I guess I should probably try x equal to 1. But oh yeah, no, that's actually not a bad choice. So let's try x equal to 1. So the limit as x goes to 1, y goes to 1 because x is going away. Let's see, 1 plus y minus 2 over 1 minus y. Well, it's going to not work out, which is going to work out. This is going to be the limit as y goes to 1 of y minus 1 over 1 minus y. Okay, help me out. What's y minus 1 divided by 1 minus y? It's a limit of -1, which is -1. Not the same. So the limit doesn't exist. So yes, it is possible to show that the limit doesn't exist via the multiple pathways method for limits that are not through the origin. It's just you have to be a little bit more creative thinking about what paths go through the point you're going through. 1, 1 and -1, 1 are pretty easy because you can often find a lot of things to go through. But look, I didn't even really have to work that hard. I could have totally ignored all of these. So if you're going through a point like 1, 1 or 1, 2, often it's a good idea to try letting y equal whatever the y value is as one of your paths, and x equal whatever the x value is as one of your other paths. That totally did it for us here. Right? We let y equal 1, we let x equal 1, we got different values. Done. It's kind of neat. As an aside, sure, yeah, fine. Just because it seemed like a good place to ask about it. I don't know what that function looks like at all. It's probably weird looking. So we have f of x, y equal to x plus y minus 2 over x minus y. You can start to talk about the domain. And the domain of the function, well, we know that we can't have this. We don't want that, so we don't want y equal to x. So we're excluding y equal to x. So the domain is everything except for the line y equals x. So here's my domain, all of that, all of that. Domain is definitely, so there's not a very good way to describe that other than it's a plane minus a line. It is definitely unbounded. And it's definitely open. Right? It does not include its boundary. Or alternatively, any point in the domain, you can find a super small circle around it that is also contained completely in the domain. Yeah. And then I also wanted to ask about the range because it seemed worthwhile. So I feel like range for this kind of question is especially hard. Although, I mean, it's especially hard, but it's also not. So let me show you how it's not hard. Let y equal 0. Then your function f of x comma 0 is x minus 2 over x. So for this particular function, can anyone tell me what single value is not in the range? What is this not able to equal? Anybody? This function has a horizontal asymptote when it's written like this. It's never going to equal 1. Right? This can't equal 1. If this were to equal 1, that would mean x minus 2 and x were the same. That's not true. So here's the way I usually look at range for something that like doesn't feel like you could really do it in sort of any kind of systematic way. Let y equal something like 0. And then ask yourself, okay, if that's the case, can I get everything? I got almost everything. I didn't get 1. Okay, could I get 1? Is there a way that this can equal 1? So let me ask you. Now that I know that I've got everything is possibly not in the range. So now let's say, well, what if this was equal to 1? are there values of x and y that can make that happen? Well, let's see. Let's multiply both sides of x minus y. So x plus y minus 2 equal to x minus y. So then the x's cancel. And then you've got 2y equal to 2. So y equal to 1. So in fact, if y is equal to 1, you totally get the value of 1 in the range. In fact, when y is 1, the function is always 1, which is kind of interesting. So the range for this is everything. You can definitely get any value in the range except for 1 when y is 0. And then when y is 1, you do get the range equal to 1. So yeah, cool. That's usually how I approach it. Like with weird fractions like this, I'm just like, okay, well, if I just set one of the variables equal to something, what range values can I get? And usually it's like almost everything. And then if you're missing something, you're like, well, can I get that by doing something else? And usually the answer is yes. Usually for fractions like this, often the range is all real numbers because it's almost impossible to not be able to get anything. I'm getting weird spammy text messages. Okay. So I think that is enough. Let's go ahead and start talking about the chain rule for multivariable functions. Which I don't remember if we talked about it last week or not, or if I just talked about it with someone in office hours. Sorry, I know. I should be able to remember things like that, but I don't. Chain rule. Okay, so the idea with the chain rule, let's actually start with this kind of chemistry example. Not that chemistry is my thing, but let's look at this one. So the pressure P, the pressure, capital P, in kilopascals, the volume, and the temperature. So volume in, I don't care, temperature in, who knows. Volume of liters, temperature in kelvins. 1 mole of an ideal gas, I don't know what that means. Probably something about compressibility, I don't really know, are related by the law. Here's what we care about. What have we got here? We've got PV equals, I feel like there's supposed to be like an NRT in there or something. I don't know what NR. I used to know. I did actually take chemistry once upon a time, but it's been a long time. So let's see what we've got here. If the temperature is 300 degrees Kelvin and is increasing at, what have we got here? 0.1 kelvins per second. If we got that, and if we also have that the volume is 100 liters and the volume is increasing at 0.2 liters per second, how fast is the pressure changing? So what we're going to do is we're going to write pressure as a function of both volume and temperature. I feel like God, man, you go through pens so fast. It's just, it's disappointing how fast it just gets used up. Anyway, I guess I can use my red pen. I got lots of other pens, but they're just not as, black ones are the best. Fine, other colors. Okay, so we're going to solve for pressure. So pressure is equal to 8.31 T over V, or maybe T times V to the negative first. And we can totally do this like the implicit differentiation way. We're like, okay, we're going to take the derivatives using the product rule and multiply by the kind of inner stuff. But there's kind of a picture we draw to make it a little bit easier. We're going to write that P depends on both temperature and volume, but then both temperature and volume depend on the variable time. Right? As time goes on, temperature and volume change. So what we're going to do to find the derivative of P with respect to time, right? Because that's what we're asking, how fast is the pressure changing as time changes. So to find dP dt, the rate of change of pressure with respect to time, we're going to find all the pathways that get us from P to time. So I'm going to go this way. So in each of these paths means we're going to take a partial derivative. So we're going to take the partial P with respect to T, and then the derivative, well, I should say a derivative. It's a partial when your function depends on more than one thing. So, right, if we're saying that P depends on time, temperature, and volume, we're going to say that we're going to have the partial del P del T and the partial del P del V. And then from here to here, we're going to have the derivative dt dt. And it's a derivative, it's straight derivative, not a partial, because t is only depending on time. So this is going to be dt dt over, and this is going to be dv dt. So the derivative of p with respect to time is going to be this times this plus this times this. Del p del t times, sorry, del p. Terrible to use temperature because you're like T's everywhere. Del P del capital T times D capital T D little t plus del V, sorry, del P del V, holy smokes, times dV dt. Which is totally what you would get if you just use the product rule, right? If you look at this, if I was going to start taking the derivative of this, I'd be like, okay, well, assuming that everything is a function of time, if I take the derivative of this, I would get, well, let's see. So the derivative first, so on the 8.31, let's just say that 8.31 hangs out. And then you would get the derivative of t, which is, sorry, I'm doing something stupid here. One moment while I don't do something stupid. Sorry, my brain is like, oh yeah, no, I'm just, yeah. Yeah, so you get the derivative of t times the not derivative of the other piece plus the derivative of v, or I should say the derivative of this piece, which is going to be -1 times v to the -2 times dv dt times the other piece, which is t. Now, this is exactly the same thing, right? If we look at this, so if you distribute the 8.31, this part right here is your, sorry, let's use this. So your dp dt is, or sorry, your del p del t is exactly that part right there. Right? If I take the partial of this with respect to t, I'm treating everything that's not t as a constant, and the derivative of this with respect to t is just, well, the derivative of t is 1. So it's 8.31 times v to the -1st times your dt dt. Plus, then if we do this part here, well, your del p del v, if you differentiate this with respect to v, pretending t is a constant, you get 8.31 times t times -v to the -2nd. There's your 8.31 times t times -v to the -2nd times dv dt. So really, this pathways method of doing the chain rule is kind of just the product rule abbreviated. Maybe not abbreviated, but reimagined. So it really is the same kind of thing either way. It's just much simpler to write it in this way. To finish the question, we would then plug in what we know. So this would be 8.31 times, so dt dt is the rate of change of temperature, which is 0.1. V to the -1st is 1 over the volume, which is 1 over 100. Plus, well, really minus v to the -2nd, so 1 over 100 squared, times dv dt, which is 0.2 liters per second, times the temperature, which is 300 kelvins. Excuse me, this ends up being approximately negative 0.4155. Negative 0.04155. That's not really the point though, right? It is interesting that it's negative. And I guess that, right, that seems certainly plausible. If pressure is temperature divided by volume, then the fact that, right, that they're both increasing means you could have the pressure increasing or decreasing. It kind of depends on which one is overpowering the other. But the real takeaway here is when we're finding the derivative of a function that depends on things that depend on the thing of the variable that we actually are interested in, we have to kind of make this pathway. So let's look at another example. Most of the time, these questions are relatively straightforward, meaning you're given a function like f of x comma y equal to, I don't know, x cubed times e to the 4y. And then you're told that x and y both depend on some third variable. So like x of t is sine of t, and y of t is cosine of t. And then we're asked to find df dt. Sometimes it's a little more complicated, but usually you've got kind of your high level thing, your function depending on some intermediate variables, x and y, and then those intermediate variables depending on the same independent variable t. So this is going to have the same pattern, right? If I'm going to find df dt, it's going to be del f del x. And your del's should really be super curly. Times dx dt plus del f del y times dy. That's how we're going to find the derivative here. So let's see. Del f del x is going to be 3x squared e to the 4y. Dx dt is cosine of t. Plus del f del y, which is x cubed times e to the 4y times 4. I'm going to write that as 4x cubed e to the 4y times dy dt, which is negative sine of t. Now, this answer is a little unsatisfying in that you're finding df dt, the derivative of f with respect to t, and your answer has the variables x, y, and t in it. If you really want your answer to kind of look like it makes more sense, you have to go ahead and plug in what x and y are in terms of t. So our final answer we could write as 3, let's see, x is sine, so 3 sine squared of t e to the 4 cosine of t times cosine of t plus 4 sine cubed of t times e to the 4 cosine of t times a negative sine of t. I might go ahead and, no, I might put the negative out front and still probably write the sine of t over here. Alternatively, although not preferably, you could go ahead and write this function f of t as sine cubed of t times e to the 4 cosine of t, and then just take the derivative using the product and the chain rule, right? So, right, it's the derivative of this, which is 3 sine squared times cosine, times the not derivative of this, which is e to the 4 cosine, plus the not derivative of this, which is your sine cubed, times the derivative of this, which is the e to your 4 cosine of t, times the derivative of 4 cosine of t, which is negative 4 sine of t. So once again, we're really just seeing this is kind of a way of writing the product. Okay, let's look at, yeah, we got time. We got time. Let's look at another example. Sure. Sometimes your function might depend on more than 2 things. So let's look at something like this. W as a function of x, y, and z is equal to x e to the y over z. And we know that x, y, and z all depend on t. X is equal to t squared, y is equal to 1 minus t, z is equal to 1 plus 2t. 1 plus 2t, James Carpenter. Now, I will again point out, if you wanted to, you could totally write this as t squared e to the 1 minus t over 1 plus 2t. And differentiate it using the product rule and the chain rule and the quotient rule. I don't think that's the way we want to go, though. You could, but the way that we really want to go is that I know that W depends on x, y, and z, and x, y, and z all depend on t. So there are 3 different paths to get me from W to t. Sorry, I'm just, oh yeah, okay. The next one, yeah, okay. I like there's something else. So, right, my dw dt is going to be del w del x times dx dt plus del w del y times dy dt plus del w del z times dz dt. Right, again, we're just finding every path from w to t. Right, if you're trying to find dw dt, you want to find every path to d from w to t and add them all up. And so whenever you go from a variable down to another variable, that's the derivative, right? So from w to x is del w del x. From x to t is dx dt. W to y, del w to y, y to t, dy dt, et cetera, et cetera. Okay, so if I were doing this, I would probably write this as x e to the y times z to the negative first. That just seems like it's going to be a little bit better. All right, del w del x is 1 times e to the y z to the negative 1. Again, remember, you're taking a partial with respect to x. X is the variable, and all this other garbage is considered a constant. So you've got a variable times a constant. The derivative of x is 1 times the constant. And then dx dt is going to be 2t plus del w del y. Okay, so the derivative of x times a constant times e to the y times a constant. Well, I know that the constant hangs out. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Okay, the derivative of y times a constant is the constant times dy dt, which is -1, plus del w del z. Okay, same deal. The derivative of constant times e to the stuff is the constant times e to the stuff. But now the derivative of the stuff, the derivative of y times e to the negative first, is the derivative of a constant y times a variable z to the negative first. That's going to be y times the derivative of z to the negative first, which is negative z to the negative second, times the derivative of z with respect to t, which is 2. Blah. And then if you really want to write your answer out in terms of t, for every x, y, and z, you would plug in t squared for x, 1 minus t for y, and z equal to 1 plus 2t. I do not want to do that. Neither do you, right? I don't want to write e to the 1 minus t times 1 plus 2t to the negative first times 2t plus t squared times e to the same thing times, right? It's terrible. But you could do that. But usually you're not going to be asked to do that. Let's do one more, maybe 2 more. Yeah, we should definitely do one like this. I got 1 or 2. Oh no, I got a few more. I don't think we're going to, so Thursday I'll try and get to the gradient and directional derivatives. I don't think we're going to get there today. One thing I want to say though, so I know this is kind of out of context, but just so you know, we'll talk about this more on Thursday, but when you're talking about the gradient, when someone says the gradient, you're like, what the heck is the gradient? If you're talking about a surface, one physical interpretation of the gradient. If you're standing on a mountaintop, or not on the top, you're standing on the side of a mountain, and someone asks, okay, James, from the point you're standing on, what's the gradient of that surface of the mountain? The gradient is the direction pointing in the steepest direction. So I always say the gradient is the direction of steepest ascent. So it's basically the fastest route to the top of the mountain. It's also the hardest route to the top of the mountain because you have to go straight up as opposed to going around and around and around. So I know it's a little not where we're at, but I felt like I should say it. The gradient is always the direction you would point at to go straight up the mountain or straight up your surface. Okay, we'll talk about, but we'll really get into that on Thursday. But I feel like we need more. We should talk more about the chain rule stuff today. Let's do a few more examples. Let's say I want to find, I need to actually write the problem. Let's say our function is z as a function of x and y is equal to the inverse tangent of x plus 2y. And we are also given that both x and y depend on the variables s and t. X is equal to s squared times t, and y is equal to s times the natural log of t. And I want to find del z del s. And it is a del because z at the base level depends on both s and t. So it's a partial derivative because, right, it's not dz ds because I can't take the derivative z with respect to s because there's another variable there, but I can take the partial z with respect to s. So let's make the little table. So let's see, z first depends on x and y. But then at the next level, both x and y each depend on s and t. So x depends on t and s, y depends on s and t. So I want to find del z del s. I have to find all the paths to s. So that's going to be this path, del z del x times del x del s, plus this path, del z del y times del y del s. So let's see what we would get. That's going to end up equaling, so let's see, del z del x. So the derivative of the inverse tangent of some stuff is 1 over 1 plus the stuff squared. So that's going to be 1 over 1 plus x plus 2y squared times the derivative of x plus 2y, which is 1, because it's the derivative of x plus 2y with respect to x, times del x del s, which is derivative of this with respect to s is going to be 2st, plus del z del y. So the derivative of this with respect to y is going to be 1 over 1 plus the stuff squared times 2, because now it's 1 over 1 plus your stuff squared times the derivative of your stuff with respect to y, which is 2, times the derivative of y with respect to s, which is just going to be the natural log of t. Well, that's kind of gross looking. You could factor if you wanted to, or you could factor out a 1 over 1 plus x plus 2y squared. And I guess if you really wanted to, you could write it as this times 2st plus 2 natural log of t. There is no good reason to do that, but you could. All right, let's look at, I don't want to do that one. That one's a little weird. We could also look at del z del t. I don't feel like it's particularly enlightening to do so, so let's not. But there's also some other stuff that's going on. So let's look at a few examples. So there's an interesting fact that these partial derivatives can be used as kind of a shortcut for implicit differentiation. What do I mean by this? Well, let's look at an example. Let's say I have x cubed plus y squared plus x e to the y equal to 7. And I want to find dy dx. Normally, in fact, let's go ahead and do it the old school normal way. So back in 21a, the way we do this is we differentiate both sides. You get 3x squared with respect to x, right? We're assuming that everything's a function of x. So 3x squared plus 2y times dy dx, plus we use the product rule here and get 1 times e to the y plus x times the derivative of e to the y is e to the y times dy dx equal to 0. Okay, so then we're going to, sorry, the line took a minute. So then we're going to group the dy dx's together. So we're going to write that. Let's see what we got here. Sorry, I'm just like keep looking at my notes. Like, okay, yeah, that's fine, sure. So I've got this and this. So I've got 2y plus x e to the y times dy dx equal to negative 3x squared minus e to the y. So then I have that dy dx is equal to, I'm going to write this slightly suggestively, it is negative 3x squared plus e to the y divided by 2y plus x e to the y. Well, here's what's kind of neat. If you look at this, see it, this is totally the negative of, well, if you took just the partial derivative of this with respect to, with respect to x, so right, if we call this function capital F of x comma y, which is usually what's done, then the partial with respect to x is 3x squared plus 1 e to the y. And the partial with respect to why am I writing the same thing? That's super smart, James. And the partial with respect to y is 0 plus 2y plus 1x times the derivative e to the y, which is x times e to the y. 2y plus x e to the y. That's kind of interesting. Here's what's really happening. So first of all, I kind of cheated a little bit on that one, because really you're supposed to bring everything to one side and have 0 on the other side. But really, as long as you have a constant on the other side, it's perfectly fine. So here's the idea, is that we've got x cubed plus y squared plus x e to the y minus 7 equal to 0. What we're going to do is we're going to say, okay, this is your function, f of xy. And we're going to differentiate it. But here's the idea. We're going to, so sorry, my brain's like, James, why are you not seeing this? I'm looking at something here that's like, sure. Oh, interesting. I see. Like, okay. So I'm like, here's the issue. So the table we would make for this, right? So f clearly depends on both x and y. But y is a function of x, right? That's the whole idea. If you're using implicit differentiation, you're finding dy dx because you're saying, oh, I'm implying that y is a function of x. I'm finding dy dx. So y depends on x. So if I want to find del f del x, if I want to find del f, or if I want to find, I should say, like the derivative of this function with respect to x, well, let's see. It's either going to be df dx, but it's also going to be, I can take this pathway as well, which is going to be fy times dy dx. So I should say, right, I've got f of xy equal to 0. And if I take the derivative with respect to x of both sides, the derivative of this side is exactly this. The derivative of 0 is still 0. And then if I solve for dy dx, look what happens. I get fy times dy dx equal to negative fx, and then divide by fy, to get dy dx equal to negative fx over fy. So that's kind of bonkers, I feel like, that you can find the derivative implicitly by saying, well, it's the, so if you want to find dy dx, it's the negative of the partial with respect to x over the partial with respect to y. Kind of interesting. I think, I mean, I was always kind of like, that seems kind of crazy, but it totally works. Yeah, it totally works. Let's do another example. I do feel like it is kind of nice because it definitely shortens the amount of work you have to do. So for example, if I was given, I don't know, where'd you go? Sorry. If I had the equation x cubed y to the fourth equal to 1 minus x cosine of y, and I wanted to find dy dx, again, assuming that y is a function of x, I can say, okay, well, first things first, I'm going to bring all this to one side. That is kind of important. So we're going to get f of xy equal to x cubed y to the fourth plus x cosine of y minus 1, and that's supposed to be equal to 0. And then we're going to differentiate, right? So we know that we're going to get that, we're going to get, we take the partial with respect to x on both sides, and we end up getting dy dx equals negative fx over fy. So the partial of this with respect to x is 3x squared y to the fourth plus 1 times cosine of y. Right, there's the partial with respect to x divided by the partial with respect to y. Okay, that's going to be x cubed times 4y cubed, or 4x cubed y cubed. And then the partial with respect to y here is going to be x times negative sine of y. I got to say that feels like a lot less algebra than taking the derivative of both sides of this, using the chain rule and implicit, then factoring out to find y prime. It seems not too terrible. Yeah. Let me show you one more example. This is because you can kind of use it for any variables. What do I mean by that? Let's say we had something that involved x, y, and z. Let's say that we have the equation x squared plus y squared plus z squared equal to 3xyz. And we want to find del z del x. Okay. So we're going to do the same thing. We're going to say that f of x, y, z. We're going to bring everything to one side. Let's bring it all to the left. So it's going to be this minus that. And that's equal to 0. So now we're going to differentiate both sides with respect to x. So we're going to take del x of both sides. So here's what we're going to get. Right. So again, right, we're imagining that our z. Sorry, this is always like, okay. Right, we're imagining that the function f depends on z, but z really depends on just x. So the idea here, and this is kind of a little bit weird, right? You're like, where's y? Well, if I'm taking the partial of z with respect to x, we're kind of imagining that y is totally a constant, right? If it's the partial with respect to x, y doesn't matter. Y is a constant. The z does matter because z depends on x. So if I want to find this, well, let's see what we're going to get here. So again, right, taking the derivative, we're going to get this pathway, fx, plus this pathway, fz times del z del x. So we again get the kind of thing that del z del x is negative fx divided by fz. It's kind of cool. It definitely works like for anything really. So if you're trying to find a derivative, partial or not, del whatever, the one that's on top is the one that's on the bottom, and the one that's on the bottom is the one that's on top, that's negative. Always works. That's going to be negative fx, which is blah. Okay, it's going to be 2x plus 0 minus 3yz over fz. Oh, sorry, it's the negative of that over the not over fz, which is 0 plus 2z minus 3xy.